Welcome to Statistical Inference. Today, we are going to explore one of the most profound concepts in statistics, known as the Cramer-Rao Inequality. Imagine you're trying to measure something perfectly, but your tools always have a little bit of error. Is there a fundamental limit to how good your tools can be? This topic will show us that the universe actually imposes a strict speed limit on statistical accuracy, and we will learn exactly how to calculate it. Now that we understand what we are looking for, let us talk about estimator variance. Imagine you're trying to guess the exact weight of a suitcase using a slightly shaky handheld spring scale. No matter how steady your hand is, the scale will always have some random bounce to its readings. In statistics, when we try to guess a hidden true parameter using data, our guessing formula, which we call an estimator, also has this natural bounce. We call this bounce variance. We want it to be as small as possible. The Cramer-Rao inequality proves there is an unbreakable floor to how small this variance can get. Before we can calculate this minimum bounds, we need a way to measure how much useful evidence our data actually contains. This brings us to a concept called Fisher information. Fisher information measures the total amount of clue or precision that a set of data provides about the hidden parameter. If the data gives us a massive amount of information, our guessing formula can be very precise, meaning the variance will be very low. Conversely, if the data contains very little information, our guesses will naturally be wide and uncertain. We find this by looking at the likelihood function. This concept of measuring evidence leads us directly to its mathematical definition. To find the Fisher information mathematically, we take the natural logarithm of the likelihood function. We then look at how sensitive this log likelihood is to small changes in the parameter by taking its first derivative, known as the score function. The Fisher information, denoted by I of theta, is the expected value of this score function squared. The expected value E represents the theoretical average over all possible datasets. By squaring the derivative, we ensure both positive and negative slopes contribute. As the steepness of the likelihood curve increases, the Fisher information increases. While the first formula is fundamental, there is also a second, often easier way to calculate the exact same Fisher information. Instead of squaring the first derivative, we can take the second derivative of the log likelihood function. The second derivative measures the curvature of the graph, telling us whether the peak is sharp or flat. We then take the expected value of this second derivative and multiply it by -1. A very sharp, narrow peak means a high negative second derivative. Multiplying by the negative sign turns this into a large positive number, indicating high information and leaving little room for doubt. Let us visualize what this second derivative actually means on a graph. Here we see two different log likelihood curves plotted against the parameter value on the horizontal axis. The tall, sharp blue curve represents high Fisher information. Because it is sharp, the data is highly informative, locking the parameter down to a narrow range. The flat, dashed red curve represents low Fisher information. A flat curve means the data is uninformative, making many different parameter values seem equally plausible. This visual intuition is exactly what the second derivative formula captures mathematically. Now that we have quantified the information in our data, we can state the main theorem. This is the Cramer-Rao inequality. It mathematically proves that the variance of any unbiased estimator, which we call T, will always be greater than or equal to 1 divided by the Fisher information. In the simplest possible terms, this formula tells us that the amount of wobble in your guesses can never be smaller than the inverse of the clues provided by your data. If your data gives you very little information, your minimum possible error will inevitably be very large. If information increases, the minimum variance decreases. This formula we just saw leads us to an important question. You might wonder when an estimator actually hits this absolute minimum floor. When does the variance exactly equal 1 over the Fisher information? In mathematics, the proof relies on the Cauchy-Schwarz inequality, which becomes a perfect equality if and only if the two variables involved have a perfect linear relationship. Therefore, the Cramer-Rao lower bound is attained only when the estimator's error is directly proportional to the score function. When this happens, we call it a minimum variance bound estimator. Let us look at the exact mathematical condition required to hit the flaw. The equation shows that the error of our estimator, t of x minus theta, must equal some constant k of theta multiplied by the score function. The constant k can depend on the parameter, but it must not depend on the data itself. If you can rearrange your score function to look exactly like this equation, then your estimator is guaranteed to have the absolute minimum possible variance. If the parameter changes, the proportionality holds, ensuring optimal precision. Before we move on, let us see this with a concrete example. We are given a random sample of size n from a Poisson distribution, which models the number of events occurring in a fixed interval. Our goal is to estimate the true average rate, denoted by lambda. We will use the sample mean as our guessing formula. To see if this is the best possible estimator, we first write down the log likelihood function for our entire sample. Then, we find the score function by taking the first derivative of this log likelihood with respect to lambda. The factorial term disappears because it acts as a constant. Continuing with our Poisson example, we need to find the Fisher information. To do this easily, we take the second derivative of our log likelihood function. The constant negative n disappears, and the derivative of 1 over lambda gives us negative 1 over lambda squared. Next, we take the negative expected value of the second derivative. The negative signs cancel out. We know from basic probability that the expected value of a single Poisson variable is lambda. So the expected value of the sum of n variables is n times lambda. Substituting this in and simplifying, we find the Fisher information is n divided by lambda. Now we can calculate the Cramer-Rao lower bound by taking the reciprocal of the Fisher information we just found. This gives us lambda divided by n. This is the absolute minimum variance any unbiased estimator can have for this problem. Now, let us look at our chosen estimator, the sample mean. The variance of a single Poisson variable is lambda, so the variance of the sample mean is exactly lambda divided by n. Because the actual variance perfectly equals the theoretical minimum, we have proven that the sample mean attains the bound. It is physically impossible to find a better unbiased estimator. Now, let us look at a case where an estimator fails to hit the absolute minimum flaw. Suppose we have a random sample from a normal distribution with an unknown mean mu and a known variance sigma squared. We want to estimate the true mean. We already know that the sample mean attains the Cramer-Rao lower bound for this problem, which is sigma squared divided by n. However, suppose a student decides to use the sample median instead of the sample mean as their guessing formula. Let us see what happens to the variance. The sample median is a perfectly valid and unbiased estimator for the center of a normal distribution. However, statistical theory shows that for large samples, the variance of the sample median is approximately equal to pi divided by 2 multiplied by sigma squared over n. Because pi divided by 2 is approximately 1.57, the variance of the sample median is about 57% larger than the Cramer-Rao lower bound. Since 1.57 is strictly greater than 1, the sample median does not attain the bound. This proves mathematically that while the median is a fair guess, it is significantly more wobbly and less precise than the sample mean. Now that we have used this formula and seen it in action, let us understand where it comes from by proving the Cramer-Rao inequality from first principles. We start with the mathematical definition of an unbiased estimator. Its expected value, written as an integral of the estimator multiplied by the probability density function, must exactly equal the true parameter theta. Next, we take the derivative of both sides with respect to theta. The right side simply becomes 1. On the left side, the derivative passes inside the integral. We then apply a clever calculus trick, replacing the derivative of the function with the function itself multiplied by the derivative of its natural logarithm. This sets up our next crucial step. Continuing our derivation, we substitute this logarithmic trick back into our integral. By doing this, we have transformed the equation into a new expected value. Specifically, this integral now represents the expected value of the estimator multiplied by the score function. A fundamental property of the score function is that its own expected value is always exactly 0. Because of this property, the expected value of the product of the estimator and the score function is mathematically identical to their statistical covariance. Therefore, we have elegantly proven that the covariance between our estimator and the score function is exactly equal to 1. This relationship is the bridge to finding the variance. To connect this covariance to variance, we use a famous mathematical rule called the Cauchy-Schwarz inequality. This rule states that the square of the covariance between any two random variables can never be larger than the product of their individual variances. We know from our previous step that the covariance is 1, so the left side becomes 1 squared. Furthermore, the variance of the score function is the exact mathematical definition of the Fisher information, I of theta. Substituting these known values into the inequality, we get 1 is less than or equal to variance of t times the Fisher information. Dividing both sides by the Fisher information gives us a final result, the Cramer-Rao inequality. So we have proven that this fundamental limit holds. Let us summarize the key takeaways from our journey. First, the Cramer-Rao inequality acts as a universal speed limit, setting an absolute minimum variance for any unbiased estimator. Second, Fisher information is the key metric that measures the precision provided by your data. The more information you have, the lower your minimum error can be. Finally, if you find an estimator that hits this bound, you can stop searching. You have mathematically proven that no better unbiased estimator exists in the universe. You have mastered a gold standard of statistical inference.